All right, back from break, and we had just taken a look at intensities and power to determine how the rate at which energy is propagated by these disturbances that we're talking about, by these waves. Now what we want to do is go in and say, let's see if we can come up with a formula that will kind of model the way that the waves are propagating. So what we do is this. What we've talked about is kind of this ideal propagation effect, where we have a profile. The profile is representing how the medium is displaced at different locations. So by looking at that waveform here, let's say it's a transverse wave passing through in this direction to the right. We could go to the left, but for now let's just go to the right. So what it's saying is each part of the medium is displaced, by a different amount at a certain instant. As the wave propagates through, we maintain that profile, and that entire profile shifts. Now, what that says is we can start with the initial profile itself at t equals 0. Let's set up a coordinate system. So we'll say that this is the x-axis, and this is the displacement axis. This is telling us how far things are displaced away from their equilibrium location. So this is going to be displacement. Initially, when t is equal to 0, let's go ahead and just use a sine function. We'll use the amplitude times the sine function. This is actually 2 pi over the wavelength. The reason for that is when x equals a wavelength, this cancels out, and 2 pi radians represents 1 full cycle. So that formula, the sine 2 pi over wavelength times x, will represent a snapshot of all the displacements that are occurring at a particular time. We're going to call it t equals 0. Now, if you remember from your math classes, the way to get a function to shift to the right, so there's a function with a profile, it's a sine function. I want that function to shift to the right, and I want it to do at a certain velocity. Now, to shift it to the right for a certain amount of time, what I want to do is subtract vt. So again, think back to your math classes. I'm thinking calculus 3a when you did functional analysis. And what they talk about, I believe in at fair length, is I can take a function, put minus some sort of a value. Now this is a variable, so it's not going to shift just one amount and stop. What it's doing is it's gradually shifting by taking the original function and replacing x with x minus vt. Now 2 pi over the wavelength, that's going to show up all the time. That's a lot of notation. What if we compress that into a new variable? So what we're going to do then with this function, now this is telling us displacement as a function of location along the medium and as a function of time. So it's keeping track of a lot of stuff. It's keeping track of the motion of every piece of the medium at all times. And what we can do is write that as a times the sine of kx minus omega t. That's the simplified version. Now what happened there? And that is that 2 pi over lambda was defined to be something we call the wave number. So the wave number has units of radians per meter, and it kind of works this way. A wave number is to wavelength as frequency is to period. So it's a different way of keeping track. If I have a large k value, what it means is that I have a lot of oscillations within a short distance. A small k value means that I have a long wavelength. Okay. Yeah. So as the wavelength gets really long, the K value gets small. The oscillations are not very extreme, but as the wavelength gets really short, K value goes up. So, you know, it's a new variable. It's something that's going to show up a lot. Make sure you're spending some time thinking about what wave number is telling us. Now, one thing that people probably, what you guys have probably are concerned about is, wait, little k, isn't that the spring constant? And no, it's not. What we're going to find out is that little k gets used for many different things. So it's not the spring constant, it's not the force constant. This is a totally different little k, and you have to be able to pick it up from context. Now, it shouldn't be too difficult because this wave number is always going to be inside a sine or a cosine function. So it's not the spring constant. If you get those mixed up on a midterm, I'm not very sympathetic about that. So make sure that you are able to pick these up from context. So what we have is a radiance frequency, which is 2 pi f, or 2 pi over the period, and we have a radians wave number, 2 pi over the wavelength. The frequency is in radians per second, the wave number is in radians per meter, and that gives us a nice, clean, compact formula with not too many things going on. Now what that's representing then is that is representing a disturbance, a wave, that's propagating. That's a wave propagating to the right at speed v. Now, if I wanted it to propagate to the left, I would put a plus sign. So a plus sign will reverse the direction and have, it will then be representing a disturbance propagating to the left. And the pattern, the wave form that we're looking at is a pure sine or cosine function. So we're back to using harmonic functions because they're the easiest ones to use when we have these oscillations taking place. Okay, so we'll imagine that this disturbance consists of one particular frequency, one particular wavelength. Now we're going to find out that's not necessarily the case. You typically can have disturbances that are a combination of different frequencies and different wavelengths, but the formula we're working with right now says there is one particular wave number, there is one particular frequency that we're considering. All right, let's try this. And so what we do is we have, now all along what we've been looking at is a traveling wave. It's a wave that's traveling, has a wave velocity to it. So here we've got, we're setting up these harmonic disturbances in this string. It says that the frequency here is 250 hertz. So I'm very skeptical now. I just don't think that person is going to be able to create 250 oscillations per second. Let's see. No, I don't think I can shake my hands back and forth 250 times a second. So anyway, that's what they're saying is happening. And also, the person is maintaining a 2.6 centimeter amplitude. So it's going, to plus 2.6 centimeters to minus 2.6 and back and forth. The linear density of the cord is 120 grams per meter. Ooh, that's kind of heavy. At t equals 0, the end of the cord has an upward displacement of 1.6 and is falling. Determine the wavelength for this traveling wave. And I'm going to do this much of the problem. I'm not, well, okay, I guess we could do this. Let's see, here's that brand new displacement formula that we just derived. What I could do is I can take a time derivative of that, and that will give me a velocity formula. Now when I take the time derivative, I'm treating x as a constant. I'm not thinking in terms of how does the wave vary from one location to the next. What this formula is keeping track of is motion of the medium. So here is the displacement formula for the medium. Here is the velocity formula for the medium. That's one time derivative. And here is the acceleration. So what that's enabling us to do is go back to chapter 14, think in terms of individual pieces of the medium and what their motion is like. Now what's different, if you think back to chapter 14, back there the kx was not there. It was just omega t. What the kx is doing is telling us as we look at different locations, and I kind of like this picture, the kx here is saying as we look at different locations, we'll see different parts of the medium in different phases of their oscillation. The whole thing's not oscillating together. Different parts are oscillating with a different type of synchronization. So it's not random, just oscillations going on. There's a synchronization, but it's a synchronization which creates the effect of the wave profile moving through the material. Now, what parts am I interested in? Some parts of this I'm not so interested in. So let's say at x equals 0 and t equals 0, well, at t equals 0, this is what the picture looks like. What they said is that we're at some displacement and that location is currently coming back towards equilibrium. The things I want to go in and calculate for this, the frequency is at 250 hertz. So what I want to do is just go in and practice what would the omega be. And omega would be in radians. I got to multiply by 2 pi. So the omega value here is 1,571 radians per second. The amplitude was given as 2.60 centimeters. Now in the example they gave us a tension and they gave us a mass density, a linear mass density. We can use those to get a wave speed. So what I'm doing here, and again, this should be kind of familiar from chapter 14, and there's even more stuff going on here in chapter 15, and that is I'm kind of running the whole list. If I'm going to use a formula that looks like this, then I've got to be able to go in and identify what each one of these constants means. So I can write this formula down. The amplitude was given. The frequency I had to calculate as 2 pi times f, but now I have it. What about the wave number? Well, that took some doing. So the wave number is equal to 2 pi over the wavelength. The wavelength is speed of the wave over frequency, and the speed of the wave is tension over the linear mass density. So I had to take the tension, the linear mass density, and get the wave speed, and then I had to divide through by the frequency and get the wavelength, and then I took 2 pi over the wavelength, and finally I ended up with the k value, the wave speed, the wave number, sorry, the radians wave number, which is 46 radians per meter. Now, let me very quickly talk about some other parts of this. This I'm not so interested in you guys worrying about. It turns out that if at t equals 0, we are not, at t equals 0, x equals 0, if the medium is not at equilibrium, then I can't use a pure sine function. I have to add on what's called a phase difference, or a phase angle, or a phase constant. And what you can do is say at t equals 0, x equals 0, that reduces down to the initial displacement, a sine phi, 1.60 centimeters. The initial speed would be using the velocity formula that we derived on the previous page. If I put x equals 0, t equals 0, that becomes negative omega a cosine phi, so it's a negative value. And then what I can do is I can use sine and cosine functions to go and determine what that phase difference would be. So if you're interested in taking a look at that, that's a little beyond what is required in the course, but there were some good parts on this example, but then the example asks some more detailed stuff, which I'm not going to worry about. If you guys want to take a look, that's fine. I'm more interested in how do we how do we do the calculations for wave number and for frequencies and amplitudes. All right. We're on to the superposition principle now, and so what we said earlier, just a little while ago, is that we don't always have one wave number and one frequency going on. So this is showing a snapshot of a disturbance, a wave, with a wavelength of this, and then here is one with a shorter wavelength and shorter. So this is disturbance 1, and this is displacement 2 and displacement 3. What happens if all three frequencies, now we're assuming they all travel at the same speed, so this would represent a higher frequency and a higher wave number. I can just look at this and say, within the same distance, this is only one cycle, this is 2 full cycles, that's 3. That's fewer radians per meter. This is more radians per meter. So the K number is going up, and the frequency is also going up. Now what happens is if all three disturbances are propagating through the same region, we'll get the combination of all three. So to a good approximation, we can just add the disturbances together. And we just get the sum of all three. This is referred to as the superposition effect. So superposition says we can just add those together. And by doing this, we can get very different looking waves. So if I take a certain amount, now they're saying here this is 1 meter of disturbance, which means the medium, that's a huge displacement. I would think this would be more in the millimeters rather than in the meters. But there's a big chunk of D1 here, and then there's a smaller amount of D2 and a smaller amount of D3, and by combining those three disturbances, they're getting something that is beginning to look like what's called a square wave. The profile, the pulse, instead of looking like a single sine function, looks like something else. So it's starting, see that blue line is showing what a pure square wave would look like. And so you could have that. You could have a disturbance that is not a sine or a cosine function. It's some other shape. Now, whatever the shape is, any periodic disturbance can be represented as some number of sines and cosines. Okay? Even a single pulse can be broken down into a combination of different sines and cosines. So that's kind of interesting that any functional shape, any functional profile can be decomposed, deconstructed into a combination of different frequencies. All right, here we're saying that we can have a wave come in and something is fixed at one point. We can get a reflection. If the end of the medium is left free so that it can kind of oscillate back and forth, then that reflection will be in the same orientation as what came in. If it's a firm, what we call a node, then it reverses. The amplitude that used to be along positive direction reflects in the negative direction. Another effect that takes place if we have an increasing density, if we have a boundary where we go to an increasing density, we can get reflections off that boundary. And so what will happen is, here is a pulse, here's a wave propagating in at some speed, and here it's going to slow down. Part of the disturbance will propagate back. So at these different boundaries too, or at variations in density, we're going to have the wave speed up or slow down. We've talked about this too. These are wave fronts. If we make the assumption that the wave is exclusively going in one direction, maybe we designate that as being the x direction. So every bit of the disturbance is propagating only in the x direction. And then what we can do is we can identify these wave fronts that make up certain planes, and we refer to that as a plane wave. Not a plane wave as being ordinary, a plane in the geometric sense. So those are wave fronts, and what the wave fronts would represent is maybe that's a maybe that's a compression. So if this is sound traveling through air, then we can say each wavefront represents a region where the compression is a maximum, and then the distance from one wavefront to the next is a wavelength. And this is often a useful way to put together diagrams to think about what's going on with the propagation effect. Now, these are curved wavefronts, very likely coming from a source back over here somewhere. And so this is more the shape of a spherical pattern. Now, once you get far, far away from the center of the source, the wavefronts start to look kind of like this, right? Think in terms of, again, think in terms of sound propagating away from a speaker. If you're very close to the speaker, then this curved effect is very prominent. But once you're very, very far away, you're only looking at a small region of this. And if I'm only looking at a small region, then to a good approximation, I can treat this as if it's just the plain wave propagations. We also get reflections off of materials, so you can have sound coming in and propagating back. Now what we find is, if we think of this in terms of the wavefronts, here's a series of wavefronts reaching the surface. Notice that this portion of the wavefront reflects first, and as a result, what we can show is that the angle of reflection matches the angle of incidence. So we're going to have a series of wavefronts perpendicular to this direction of propagation. What they're calling the ray is the direction of propagation. And then here is the incident direction of propagation. And these angles are measured relative to the normal by convention. And we say that the angle of reflection matches the angle of incidence. You can try this with sound, right? The San Francisco Symphony, I know, has all those really pretty reflective surfaces hanging up above where the symphony plays. And the idea of that is to redistribute the sound through reflection, is my understanding. All right, superposition. The fact that when we have more than one wave crossing through a region, and we can just add the effects of the waves, that creates some interesting effects. Let's say we have a string, and we create a single pulse from each end in opposite orientation, and we send those pulses past each other. What's going to happen? So initially it looks like this. Here are two pulses approaching. Superposition says if this pulse is the mirror image of this pulse, that there's going to be a time right when they're completely overlapped when the string, the medium, just goes flat. But superposition also says that this pulse will reemerge going in that direction, and the lower pulse will reemerge going that way. How can that happen? It was flat at this region. Well, the displacement here was 0 at every location, but not the velocity. So even though we've got this nice snapshot where superposition said this and this combined undergoes what we call a destructive interference effect. So when this superposition takes place, we refer to that effect as interference. It's interesting because there's like, interference sounds negative, right? It sounds like not a good thing. But actually interference can be constructive. So maybe they should call it superposition instead. But we use the word interference to represent what happens when we superpose different waves. And here, as these two pass each other, this region of the string it has different velocity. And so this part of the string is all ready to move back up, and this part of the string is all ready to move back down, and that's why these two pulses reemerge. This is kind of fun to try out and see that they really pass through each other. Now this is a destructive effect is what it's called. It's a destructive interference effect. This is called a constructive interference effect, and that's because when we send two pulses with the same orientation, when they overlap, they generate momentarily this higher amplitude wave. Okay. Now we can also represent this mathematically, so we can just go back and start adding some of these waves together mathematically and predict what's going on. So in general, if we have, here are two disturbances with the same wave number, the same frequency, crossing through the same region, and they constructively interfere with each other, these are exactly out of phase, and so if these pass through the same region, we'll get nothing. Okay, so this is kind of like a sound canceling device. You know, if there's a loud sound outside, you can get these headphones that sample the sound and very quickly generate an equal, well, the mirror image of that sound that's occurring, and then it sends both to your ears. So it takes the sound from outside, well, it doesn't take the sound, but the sound from outside is coming in through the earphones, but the earphones are generating an anti-effect, and it minimizes the, cancels out that effect. Now this is something intermediate. So you can either have, you know, identical matching constructive interference, exactly out of phase destructive, and then there's everything in between. So it's important not to forget the everything in between. All right, now we've been looking at traveling waves. Let's take a look at what are called standing waves. And this almost sounds like an oxymoron, right? It's like, wait a minute, waves propagate. How can you have a wave that's just standing in one location? Does that make any sense? And it clearly happens. I mean, observationally, if you take a piano string or a guitar string or something, and you fix the ends of the string and you pluck it, the string vibrates. And if you take a close look, maybe with a strobe light or something, and with good lighting effects, you can see that what the string is doing is all parts of the string now are synchronized so that they're moving back and forth together. Now also what you see is that the amplitude is not the same at every location. The amplitude varies, and what we're going to show is that the pattern that we get for a particular standing wave is a sine function. It's a sine or a cosine function. We're going to be using sines. It's easier to view that way. Now, not only is this vibrational mode possible, but what we find with standing waves is, again, if I create a node here by fastening the string, I create a node here by fastening the string. Now, the only reason the person still has their hand there is to keep the vibrations going, but let's treat this as a node. This is a node. This is referred to as an antinode. I think that's brilliant. You know, what do you call the place where the amplitude is the very largest? A node is where the amplitude is 0. Oh, let's call it an antinode. So you can also set up standing wave patterns with a node in the middle where nothing's holding it in place, except that in this case, the two different parts of the string are oscillating opposite to each other, and so there's always a set of forces holding that node in place. That turns out to be a real thing. So you can actually have these nodes that are sustainable. The nodes just stand there, and they're just there because of the pattern of oscillations. Now, we refer to this as the fundamental frequency, or the first harmonic. We call this the second harmonic. This is the third harmonic, and here we've generated a couple of intermediate nodes. So the name of the harmonic has to do with how many antinodes. This is one antinode, it's the first harmonic, two antinodes, second harmonic, three antinodes, third harmonic. And so in this one, just the third one, so the ends would be moving up and down together, but the one in the middle would be behaving oppositely. And that's how the nodes are maintained. So kind of interesting that we've got these standing wave effects. So here we go, first harmonic, second harmonic, third harmonic. They're calling this the first overtone. That's a little confusing, but I think they use that in some of the homework problems. You have to be ready for this. So either first, second, and third harmonics, fourth, fifth, sixth, or fundamental, first overtone, second overtone is another way to describe those. Now, the wavelengths here, in this case, the wavelength is actually 2 times L, where L is the length of the string. Because all I have here is half a wavelength. A full wavelength would be 2 of these. So the wavelength here is 2L. The wavelength here is 2L divided by 2. The wavelength here is 2L divided by 3. So we can develop for these standing wave patterns, these are the possible solutions, we can come up with some formulas. We can say that the nth harmonic, where n can equal 1, 2, through any integer number, for the nth harmonic, the wavelength is 2L divided by n. And we can show pictures of why that is. And that's the kind of stuff I ask for on midterms too, is not just plug numbers into a formula, but show me the pictures of what's happening. So show me the diagrams of what these different harmonics look like. So be prepared to draw the first, second, third, and fourth harmonics and give some indication of what that represents. Now the frequencies of these oscillations, the frequency at which they're oscillating back and forth, is given by the wave speed divided through by the wavelength. That's a formula we've used before. And that means, substituting some stuff in here, that is going to be the wave speed times n over 2L. Now the wave speed depends on how I set up my string. It depends on the tension that I've placed in the string. It depends on how heavy the string is. This is like a guitar, right? If I am building a guitar and tuning it, and I want the string to oscillate at a certain frequency so that it generates a certain pitch, pitch is frequency, then what I want to do is I want to build it with a string with the right mass and length, and then I want to tighten it to the proper tension so that I'm getting a wave speed that I have control over. And then the length of the string will determine wavelength, and so that's wave speed over 2L tells me what my frequency will be. It tells me what the fundamental frequency or first harmonic will be. Now what this formula is telling us too, this factor then, says if I look at the pattern of frequencies, this is going to be the first frequency. The first harmonic will have a certain frequency, F1. The second harmonic will have a frequency that is twice as much. And the third harmonic 3 times as much, and that pattern just continues. So what's happening here is the frequencies of the oscillation, of this standing wave oscillating back and forth, is going to vary. And it's going to vary according to how many antinodes we have in that pattern. So that means that we're going to get a series of frequencies for this string that are all multiples of each other. Okay, so let's take a look at a piano string and run some numbers on that as an example. So we have a piano string. It says that it's 1.1 meters long. It's got a mass of 9 grams. The fundamental frequency we want to be 131 hertz. And then what will be the first 4 harmonics? Harmonics 1, 2, 3, 4. That's the first harmonic, is the 131 hertz. That's what they're asking. So let's take a look. So this is what the first harmonic standing wave pattern looks like. Now the length was 1.10 meters, the mass was 9 grams, the frequency that we want is 131 hertz. It's the first harmonic, so n is equal to 1. That says the wavelength, a formula, 2L over n, says for a length of 1.1 meter, the wavelength is actually 2.2 meters. Now the wave speed, you know, when we went and used this formula, the wave speed is equal to the frequency times the wavelength. I plug those numbers in and I find out the wave speed is 288 meters per second. And then that gives me pause because I think it's a standing wave. It doesn't have a wave speed, or does it? Now what we can show mathematically is that a standing wave is the equivalent of two different wave effects propagating from opposite directions, and in the region where they overlap, the superposition will give us a standing wave. So we can actually show that mathematically if I take two different disturbances and overlap those, and then take a look at the pattern of displacements, that creates a standing wave. So it's kind of interesting that even a standing wave will have a speed of propagation to it. So we do have a speed of propagation for this standing wave, and it's given by t over mu to the 1/2, and that says the tension that we're trying to calculate here. The tension will be given by taking mu times v wave squared. So now the mu value we get from taking the mass and dividing by the length, 0.00818. Remember, this has got to be in kilograms per meter. Everything's got to be in a standard unit. So, so we've got the mu, we've got the wave speed figured out. We can put those together into our formula, make sure this gets squared, and it says the tension that we're going to have, the tension we're going to need to create this frequency with this string with these properties. The piano string needs to be tightened to 680 newtons. That's a lot. That's like 120 pounds of force or something. So that string is really, I think the string's going to snap. Anyway, that's what we ended up with, is a tension of 680 newtons. Now, if that's too high of a tension, we could go back and make some adjustments. We could get the strings to be thinner, and then the mu would be less, and the tension wouldn't have to be so high. So if you keep snapping those strings when you're, tuning your guitar, maybe you need a different thickness of string instead to work from. All right, I think we got everything covered. Let's see, there was a part B on this too, right? And part B said, now let's take a look at all four of the harmonics. The first, we tuned the piano's string so that the first harmonic was at 131 hertz. We've kind of gone through all this. Maybe we'll go back through it very quickly together again. The second harmonic will be twice as much, the third harmonic, the fourth. I just have to take that first number, multiply by 2, multiply by 3, multiply by 4 to come up with all of the other values. Now, so it's a good review actually. So let's take a look at it. Remember, the wavelength can be determined for each harmonic can be determined by 2L over n. N is an integer value. The wave speed is going to be related to the frequency times the wavelength, and that tells me how to determine frequency. So frequency then we can determine by taking the wave speed, dividing through by the wavelength. Now the wave speed is determined by t over mu to the 1/2, and the wavelength is determined by t2L over n. That gives me a frequency formula of 1 over 2L t over mu square root. That, if I'm tuning my guitar, tuning a piano string, that formula will allow me to go in and determine how to bring together all the effects. I have to work from the length of the string, the linear density of the string, and then the tension in the string. That will determine the frequencies. Also, what we can say is if this is the first frequency, all the other frequencies will just be a multiple of the first harmonic. Okay, so that's an interesting set of patterns to think about. Now, here is an example. Let's see, we've got I don't know what the picture is telling us. This is a little confusing. I'm not sure what the picture is doing. Anyway, the example says this. It says, what would happen if we took two traveling waves, traveling wave 1, traveling wave 2, and we take their formulas. They both have the same amplitude. They both have the same wave number. They both have the same frequency, but they're traveling in opposite directions. Now, we kind of hinted around at this. What's going to happen if I algebraically combine those two together? So let's take a look and see. This is what's going on. We've got these two different disturbances crossing each other. Now, they don't have to be transverse waves. These could be compressions. So you could have compressions also. It could be either one. This is like a guitar string effect by creating a standing wave from two traveling waves. Or if it's a, if it's a woodwind instrument, then you're setting up these standing waves of compression, and so those would be longitudinal. In any case, we can represent either one by these functions. This is our displacement as a function of position and time at every location along the string. And then these are two sine functions, and they only differ by the plus and minus here. Now, there is a trig identity, and I know whenever I say trig identity, students, sometimes that was very traumatic. Trig identities they're tough. That's a difficult area of mathematics. Anyway, there's a really handy trig identity that says if I take the sine of something and the sine of something else and add them together, we can show, I can't show, I mean, I would have to spend the rest of today showing this. Anyway, if I add those two together, I'm going to get 2 times the sine of the sum, theta 1 plus theta 2 over 2, times the cosine of the difference, theta 1 minus theta 2 over 2. Now, if we take those two expressions and we say theta 1 is kx minus omega t, and theta 2 is kx plus omega t, and plug into those formulas, when I add those two arguments together, the omega t's cancel out, and I get 2kx divided by 2, which leaves me with kx. When I take the difference between them, the kx's cancel out, and I get minus 2 omega t divided by 2 leaves me with minus omega t, and the cosine is an even function. So cosine of minus omega t is the same thing as cosine of omega t. So this is our mathematical proof, or our mathematical representation of how a standing wave is the equivalent of two traveling waves going in opposite directions. So it's superposition, right? If we can generate a disturbance, a wave going into the right, and we can create a disturbance of the left, then we can create both at the same time, and that's the equivalent of a standing wave. So we do have a wave speed associated with the standing wave. We've added these two together here, and what we're seeing is, well, this is what's happening on the standing wave. The space factor now is separate from the time factor. It's no longer traveling, because it's not kx minus omega t, it's the sine of kx, that's the profile, times the cosine of omega t, which represents how that profile is oscillating back and forth in time. So the entire profile oscillates back and forth in time. The nodes don't move. So wherever the nodes are, they stay fixed. And that's how a sine function would work if it's standing instead of traveling. Okay, so let's put the numbers in. I guess that's what happened. They gave us a bunch of numbers. So this is what we calculated by adding the two traveling waves together. The amplitude is 20 centimeters. The wave number is 2.0 radians per meter. That gives us a wavelength. Just out of curiosity, I looked at the wavelengths. 3.0, maybe they asked for it because I boxed it. So the wavelength is 2 pi over k, 3.14 meters. The frequency is 4. I'm reading that off the information that was given, right? So, and again, I always prefer writing this as A and then off to the side saying A equals this. Write that as a K, write that as omega. Putting numbers in, I think, makes things more confusing. That's my personal opinion. That's my, from my experience. All right, so what we've got then is we figured out the frequencies, the periods, and the Hertz frequencies. So we've got all of those. And then it says, at a position of x equals 0.45, go in and calculate the displacement. So I'm taking that formula, substituting in 0.45 meters, substituting in 0.45 meters for x. Now they're saying what's the maximum amplitude. So we're just going to go ahead and say t equals 0. That's one of the times at which the amplitude would be at a maximum. So that would be, that factor equals 1. And then I got to put in the kx. So I put in the k value, 2 radians per meter, and I put in the 0.45 meters, and I set my calculator to radians. Don't forget, this is in radians. So the sine of this became 0.783. Now 2 times the amplitude is 40 centimeters. So it says that the maximum amplitude would be 40 centimeters, which is a lot. 40 centimeters of amplitude. This thing is oscillating back and forth like this. And then the displacement at this particular location, the maximum displacement, is 31 centimeters. So the 40 centimeters would be at one of the antinodes. The 31.3 centimeters is at a location of 0.45 meters. Is how it works. All right, we can also have an effect with waves called refraction. We're kind of back looking at, here comes an incident wave, here come these wave fronts. Now these wave fronts slow down. See how we've got a broken wave front here? The wave front, this one's traveling at a higher speed out here, and then maybe this one's traveling at a slower speed. So it's not air going into water, because air going into water would be opposite to this. So if it's air going into water, they've got it backwards. They've got it going from a medium where it's going faster into a medium where it's going slower. And so what we can do is we can go through and we can do a little geometry on that. Here's their close-up of what's going on. They've gone through and identified a couple of triangles. What I prefer, I should have added this in. We need another arrow right here. I should go back and add an arrow in and show that we have this sound coming in. It travels slower once it's gone into this medium. It continues to travel faster here though. And then you get these two triangles. They're both right triangles. They both share a hypotenuse, and from that we can do a little bit of geometry. We can show that the sine of theta 1 right here with these wavefronts is this distance, L1, which is V1 times T. So we're saying during a certain time interval, when the sound travels from here to here, this part of the ray located here, is traveling a shorter distance. And so it means that the wavefronts then will get shifted. So they had those nice pictures with the wavefronts kind of broken, showing as they go into this new material and they slow down. Now it does, it feels kind of backwards. It's like going from water, where you're going faster, into air, actually. So maybe it's, I'm not sure. Maybe it's going from steel into wood. I don't know. Something like that. All right. The sine of that is the opposite over the hypotenuse. That's L1 over A, which is V1T over A. Don't need to know the derivation on this, but I will go through this just to talk a bit about what's going on. And then theta 2 is this distance, which corresponds to the same amount of time but the distance is shorter because the wave has slowed down at that location. And that's Vt, V2 times t over a. When we take that ratio, the times cancel out, the a's cancel out, and what we find is that the side of the angle on each side is equal to the ratio of the sides of the angle is equal to the ratio of velocities. So again, probably the easiest way to see those angles, this is theta 1, this is theta 2, 1 and 2. And so the sine of those angles are proportional to the velocity in that region. So where the velocity is higher, the angle will be higher. Where the velocity is lower, the angle will be lower. Okay, so here they've got another earthquake. It's passing a boundary in the rock where it goes from a slower speed to a higher speed. Let's take a look at the effect. So here it is traveling through some kind of a rock, and then it hits a region where the rock is denser. Or maybe not where it's denser, I guess where it's stiffer. So the speed goes up. So what we can do then is say that the sine of the angle the ratio is going to be equal to V2 over V1. And they've given us that. So they said in material 1 it was traveling at 6.5 kilometers per second and 6,500 kilometers per second. And here's traveling 8,000 meters per second. So what's going to happen is that in the faster material, the angle will get bigger. I mean, we got to be able to see that conceptually, identify that on the diagram. And then, so draw the diagram first and see how that refraction effect occurs, and then go back and do the math. Now, when I did the math, I'm predicting that the ratio of the sines should be 1.23, and then they told us that the initial angle, theta 1, is 30 degrees, so that came out to be 38, and yeah, that kind of agrees with what we expected. We expected that, you know, the velocity went up, not a lot, but it went up significantly, and the angle did kind of the same thing. Now there's also an effect with waves called diffraction, and this effect has to do with the size of the object and then the wavelengths. If I've got wavelengths that are pretty short compared with the size of this object, notice the shadow region that we have behind it. That's a diffraction effect. It's an interference effect that's taking place in that region. And then what they're showing with this picture is here are some water waves coming through individual pieces of grass. Here is a stick in the water. There's a diffraction effect here. Short wavelengths are passing by this log that's floating in the water, and then we have some longer wavelengths. And when you have these different effects, you're going to have different shadows, different diffraction shadows that show up. So the amount of diffraction depends on the size of the obstacle compared with the wavelength. If the obstacle is much smaller than the wavelength, we won't see much of an effect. So in that last picture, I don't know if they completely did it, but the wavelengths are so large and the obstacle is so small that we're not seeing much of an effect. With the smaller wavelengths coming in with that larger object, we are seeing an effect with those smaller wavelengths. Those are tending, in this case, the wavelengths are actually almost able to wrap around this. So they kind of wrap around and realign on the other side. And here, with the shorter wavelengths, that doesn't happen. Okay, that's it. Chapter 15. So if you guys have questions on any of this, go back and find a nice picture to finish on. Oh, there are no nice slides in this chapter. Okay. Anyway, let me go back to the other end then, and we will just leave this at the last picture. Okay, let me know if you guys have any questions. Stop by office hours and we will take a look at those.